Hey, welcome back, my little statistical outliers. How are you doing today? We are going to talk about one-dimensional accelerated motion. Don't worry, we will definitely get to two-dimensional accelerated motion. And we're never going to worry about three because three is really just a special case of two in most cases. Of course, that's not 100% true. But most things I teach you in this class are never 100% true. So, sorry for lying to you. But we're going to start off easy. We will get to two-dimensional motion, and then the problems tend to explode out of control very quickly. So I want to make sure you have a firm understanding of what it means to accelerate, and then we'll trip about how to accelerate two ways at once. All right. All right, cool. So let's talk about vocabulary. You've only got to learn one new word, and it is acceleration. So acceleration is the rate of change of velocity, and it's how quickly an object is changing speed. You want to think about acceleration as speeding up or slowing down. Look at my beautiful cursive. Anyway, these are the two that you want to really solidify in your brain. We're gonna add a third component to what it means to accelerate in one slide. But that's the basics to get a handle on. That's how we're gonna grip this thing to come to terms with it. And then we'll find some more handholds later to sink our teeth into. But for right now, think of it as speeding up and slowing down. Acceleration is a vector, like most useful things in life. And we're going to measure it in meters per second per second. Let's break this down and then we'll do math simplifications. Okay. It's the rate of change of velocity. So let's say my velocity starts off at 3 meters per second. And then I'm going to accelerate. Whoops. Back that up. Oh, go forward. We're going to accelerate at 1 meter per second per second. So what this means is at time 0, we're at 3 meters per second. 1 second passes, we're at 4 meters per second. 1 more second passes, we're at 5 meters per second, right? So we gain 1 meter per second each second. So meters per second is the unit of acceleration because it's measuring the rate of change of our velocity. Okay. Let's talk about fractions real quick. If you have meters over seconds, instead of dividing by this, you can flip and multiply it. So it can be meters per second times, well, this isn't a fraction. Let's make it a fraction. So 1 over seconds. So this is meters over seconds squared. This is how you're going to see it written. And I will 90% of the time say meters per second squared. But realize that this maybe doesn't tell the whole story. This is a better way to think about it, meters per second. But this is nicer and easier to say. So this is how it's going to get said, and this is how it's going to get written. But you need to remember the physical meaning of acceleration. Okay, so let's go look at some problems. We're going to talk about a misconception, and then we'll look at some formulas, some practice problems, and then we'll send you on your way to struggle through it on your own. All right? So let's talk about this misconception really quick. It says, a car is initially traveling north on the 101, and near Union Hills, it gradually follows the curve of the freeway and is now headed east. The speedometer says This is maybe not worded very well. The speedometer stays at a steady 65 miles per hour the whole time. So let's draw a little picture to really illustrate what we're talking about here, right? If you're familiar with the greater Phoenix metropolitan area, there's a freeway called Loop 101, and it does, I don't know what it does really down here. It does some stuff, but over here's where we're talking about. So you're cruising along the highway in your car. What do cars look like? Right. So you're cruising down the highway. Anyway, that's getting ugly quick. Anyway, okay, we'll leave it at that. You're cruising down the highway. Once you get to about here, I think this is like Union Hills or so, your freeway will curve around, and then you're going to start headed east towards Scottsdale over here. And you don't ever want to go there. This is like what Mufasa warned Simba about. Don't go to Scottsdale. Over here, the freeway curves. The whole time you're cruising around, your speedometer is at a steady 65 miles per hour, because that's the speed limit, and we don't want, it's actually a little higher than speed limit, I think. I think this is speeding, even though people on the 101 probably go like this. A little closer. Anyway. So as you drive around this curve, your speedometer says 65 miles an hour the whole time. The question is, did the vehicle accelerate? Now let's think about this. Acceleration is the rate of change of velocity. Okay, so the obvious question here we should ask ourselves is, did we change velocity? So this question is the same as, did velocity change? That's the question we're really answering. Did our velocity change? If it did, then yes, we accelerated. If it didn't, then no acceleration happened. So did the velocity change? It says we're going 65 miles an hour the whole time. But we need to remember, velocity is a vector. So walking or driving 65 miles per hour north does not equal going 65 miles per hour east. These are not the same thing, because while the magnitude of our velocities is the same, the direction is different. So if the direction is different, they're not the same, ergo, a change did happen. Did the velocity change? Absolutely. Okay. So we definitely accelerated, even though we didn't change speed, we changed velocity. So we need to go back and amend this. We're thinking about it as speeding up, slowing down, and turning. If you change the direction you are moving, even if you do not speed up or slow down, you still changed your direction of velocity and you accelerated. Super important. That is one of the most important ideas in physics. We will have a whole unit just around the idea of turning later. So let's hammer that out now, shall we? Okay, cool. So we hammered out that misconception. If you ask like your dad or someone and you're like, hey dad, if you drive around the 101 and you go 65 miles per hour the whole time, did you accelerate? And he'll be like, heck no, boy. And he'll be like, wrong, bucko. You did, because you turned. It's incredible that you and your father have such a well-hidden Southern accent, but I digress. All right, let's talk about some new equations. So let me first amend our displacement equation. Our displacement equation used to be that. Velocity initial times time plus our initial displacement. Okay, this was our displacement equation. This was only good for constant velocities, and we talked about that when we looked at the problem where here's your velocity, here's your time. When we looked at this problem, we could do this problem graphically by finding the area of this little rectangle and finding the area of that triangle and adding them together. But when we tried to use our formula, we saw that the formula does not agree with the area under this velocity. That's because this displacement equation that we have so far is only good for constant velocities, and the velocity is not constant, it's increasing. So what we need to do is we need to add this triangle on top. We saw that this really only tells us the story, hang on, I need a prettier color, of this rectangle right here. And we saw that we didn't account for this entire triangle, which is a huge part of the graph, using this equation. So we need to amend it. To get this triangle on top, we're going to add this term to the front of our equation. So what this term is how we kind of correct for this triangle. And the term is 1/2 acceleration times time squared. And now you're going to say, Mr. Barton, displacement initial, velocity initial, ¿por qué no acceleration initial? And you've got me. Technically, yes, this is initial acceleration. However, we are not going to look at problems where the acceleration is changing unless it's changing in a super special way where this doesn't even really make sense to use anyway. So you're right. We should be using acceleration initial, but you know what I mean? It's not going to come up in this class. If we are going in straight lines, we're either going to break stuff up into components, which is way later, or we're going to be moving in a special way where this whole equation doesn't even really apply anyway. So this is the long way of telling you, don't worry about it. Okay. Okay. There you go. Just put that on there. Forget this equation, add this equation. In fact, this equation simplifies to the old one when acceleration equals 0. If acceleration equals 0, 0 times 1/2 is 0, and then 0 times any other number in the whole world is 0, and this whole thing zeroes out, and 0 plus stuff is the stuff. So it goes away and it's not important. So again, if our velocity is constant and we are not accelerating, it turns back into the one you know and love. But now we need this extra term on here to fix it for if we are accelerating. All right. Now we also need a velocity equation. So right now you have just the average velocity equation, which is change in position over change in time. This is average. This is not really going to get us a final. It's going to give us an average, right? So if we are accelerating, we want a way to figure out how fast will I be going after a certain amount of time. So we have this velocity equation. Let's break this bad boy down. Velocity final, okay, that's an output, equals a rate of change times some input variable plus the starting point. Whoa, that's so crazy. It's just y equals mx plus b again. Just like this used to be y equals mx plus b. Are you noticing a pattern here? Kind of crazy, huh? So this is now a quadratic because we have a squared term on it. Now we have a linear equation for this, and then we're never gonna get we're not gonna get an acceleration equation. This thing's not useful. Okay. Now listen up. I understand that you've been listening the whole time, but you need to like actively listen now, I'm going to tell you something that is someday going to get you at least 2 free balsamic flatbread pizza appetizers at your local dining establishment. Okay. We have displacement. The rate of change of displacement is velocity. The rate of change of velocity is acceleration. How deep does the rabbit hole go? What's the rate of change of acceleration? Write this down. This is how you get free flatbreads. I've gotten so many free appetizers at Trivia's because of knowing this fact. The rate of change of acceleration is jerk. Like, you're a jerk. You're a jerk. You know what I mean? Do people still listen to that song? Probably not. I didn't rap it correctly either, but anyway. Okay. Rate of change of acceleration is jerk. Like a jerk chicken or like yep, that's the only place people use the word jerk. Cool. Let's go a little deeper, though. The rabbit hole goes pretty deep, and it gets kind of funny. It really, I think, hammers home how uncreative physicists are. So, rate of change of acceleration is jerk. Rate of change of jerk is snap. Here's where it gets weird. Rate of change of snap is crackle. And the rate of change of crackle is pop. And this is real physics. You can Google that. I'm not fibbing. Google it. When I found this up, I almost changed majors. I was so livid. I was so angry. I was like, physics is a joke. But anyway. Memorize this. This is good for trivia. Someday you'll be old enough to go to trivia at places that serve beverages and appetizers and ask trivia questions. And specifically this one, is a really like famous one. I don't know. It shows up in trivia all the time. And they're like, here's the bonus question, science. And then everyone in the whole dining establishment groans to go, oh, I hate science and math, you know? And then you go, no, I took high school physics. And then you write this answer down and you go hand it to the trivia person. They're like, you win the free appetizer. And then you get free flatbread pizza. I've gotten like 6. Cool. All right. I've wandered enough about these. Okay. So here's our 2 new equations. We're adding this term to make it so that our displacement equation works for things that speed up and slow down or turn. And we now have a velocity equation so that we can figure out how fast stuff is going at the end. Let's go use these just so you can see the inner machinations of physics. Okay. Here's a velocity example. A car is driving at 20 meters per second initially. This is about 45 miles an hour, maybe a little slower. Then gradually accelerates at 3 meters per second squared, or 3 meters per second each second, for 15 seconds. How fast is the car going after 15 seconds of acceleration? This is like baby physics problem, but we're going to do it because we need baby steps to get us going. So read the question. How fast, what are we asking for? Not displacement, but velocity. Is the car going after velocity final 15 seconds? So we need to find final velocity. Our final velocity equation is final velocity equals acceleration times time plus initial velocity. Let's go back and read the question and pick out some variables. A car is driving at 20 meters per second initially. Initial velocity. Then gradually accelerates at 3 meters per second squared. Acceleration. For 15 seconds. That's a time. Wonderful. Now we plug these things in and you're doing math. So V final, we don't know it. We'll leave it as a variable. Let's change to teal. V final equals acceleration let's just check our units. Meters, seconds, seconds. Everything looks the same to me, so we're good to go. Acceleration is 3. Time is 15. Initial velocity is 20. So V final is 3 times 15 is 45 plus 20. V final equals 65 velocity. So we're measuring that thing in meters per second. This is really fast. This is like 130 miles an hour. So don't drive that fast, but it's not important. Maybe it's a dog or something, you know. All right. So that's the easy baby question. That's just to get started, show you where stuff goes, kind of, you know. Let's go do like a real AP physics question now. You can tell this is a real AP physics question because it ends with 3 questions. That's how AP physics exams tend to be. They'll give you one situation and then ask you 3 or 4 questions about it. Because physics is complicated. It's not just one and done. You got to ask 2 or 3 questions to really hammer home the point and get to what you want to know. So be prepared for multi-step questions. This is maybe one of the harder questions we've seen in this class so far. So buckle up, put on your big boy socks, and let's investigate. So it says Antonio is skating into a headwind. And if you don't know what a headwind is, it's the worst thing on the planet Earth. It's where the wind is blowing into your face. If you know anything about running or riding your bike or trying to travel by any means where you power the locomotion, headwinds make you wish that, I don't know, I can't think of anything school appropriate, but they make you think unthinkable thoughts for sure. So he's skating into a headwind, so he's hating life. Initially, Antonio is traveling at 3 meters per second. The wind is pushing on him, causing him to accelerate backwards at 0.5 meters per second squared. That sounds important. Just to see what happens, Antonio doesn't kick. So he straight up gives up on skateboarding. He's like, I can't do it. He doesn't kick anymore and just lets the wind blow on him. You know, he's going with the breeze. How fast is he going after 6 seconds? After 8 seconds? So we'll also find after 8 seconds. And how far does Antonio go or move during those 8 seconds? Okay, so let's read the questions and see what we're looking for. How fast? That sounds like a velocity. After? That sounds like a velocity final. Okay, so we're looking for V final twice, right? We're going to do it for 6 seconds and 8 seconds. Those are times, right? So T equals 6 and 8 seconds each time. We'll plug them in separately, but you know. All right, equations. V final equals V initial plus acceleration times time. I realized I just swapped the order of this, but again, addition is commutative and the order of adding things doesn't matter. So let's go back. We need to find any initial velocity. We kind of already have our times and then an acceleration. So he is initially, right there, initially traveling at 3 meters per second. So V naught is 3 meters per second. The wind is pushing on him, causing him to accelerate backwards at 0.5 meters per second squared. So acceleration is 0.5 meters per second squared. But let's maybe draw a picture and look at something. I find that drawing a picture for physics is incredibly helpful 90% of the time. So let's see. And it doesn't even have to be that complex, right? Frowning because he's got a headwind. So the wind is blowing on him like this. Okay. He is moving in that direction. Our V initial is 6 meters per second forward. I'm going to say to the right is the positive direction, and to the left will be the negative direction. Okay. So his velocity is 6 meters per second forward. His acceleration, let's pick a different color. Let's do It's a pretty blue. That's kind of an ugly blue, but oh well. Is 0.5 meters per second squared backwards. The way we're going to quantify backwards is we're going to make that bad chicken negative. So acceleration is negative because of the direction it's pointing. Like I said earlier, most of the time we indicate a vector, or rather its direction, is by sign of a number. So by putting this negative sign on this number, we have really vectorized our acceleration. This is super important, especially if we want to use equations. Okay, so we have our initial velocity, our acceleration, and our 2 times. Now we can use this equation to find v final. So let's go do that. So v final equals, we'll do 6 seconds first, is initial is 3 meters per second plus negative 0.5 times our time is 6. All right, now we're going to multiply. Negative 0.5 times 6 is negative 3. 3 minus 3 is 0. So V, I'm going to put, instead of F, I'm going to put 6 to show us it's 6 seconds, is 0 meters per second. All right, let's do 8 seconds. V8, or V final, equals 3 initial meters per second plus negative 0.5 times 8. So after 8 seconds, we're going to be going 3 minus 4. We're going to be going negative 1 meters per second. All right, let's talk about a couple of things, because this brings up another important misconception that we need to wrap our brains around. And we need to physicalize this answer. We need to get a visceral understanding of what this means, not just what the answer is. Then we'll go back and do one last calculation to figure out how far. Okay, so V6, or after 6 seconds of accelerating, Antonio is going 0 meters per second. This means stopped. Okay, so every second we're going to lose half a meter per second. So every 2 seconds we'll lose 1. So let's look at something. Let's do time. Let's do velocity. Okay, so 0, he's going 3 meters per second. I'm going to do it in increments of 2 seconds, because minus 1, right, is 2 meters per second. 4 would be 1 meter per second. 6 is our 0. And then 8, we're going negative 1. Let's look at this really quick. We could even go so far as to graph this, right? Here's velocity. Here's time. At 0, we're at 3. So 1, 2, 3. Yep. So 3, 1, 2, 3, 4, 5, 6. And these are 2s. So 2, 4, 6, 8. Anyway. So 3, 2, 1, 0, negative 1, probably negative 2. Oh, that's so ugly. Try one more time, sir. That's way better. You can tell I can't draw axes very straight. But, okay, let's talk about something. While his velocity is positive, positive velocity means moving in the forward direction. So this is moving forward. This spot right here, when velocity is 0, this is stopped. Okay, so the wind's blowing on him. He's slowing down, stops. And then what happens here? What does negative 1 meters per second mean? What this means is that he has stopped. The wind continued to blow on him and starts to push him backwards. This means moving backwards. How interesting. Maybe not, right? It's very intuitive. It's very obvious what should happen, right? If you are being pushed on something that rolls around. You're going to slow down, and then it's going to push you the other direction. But I feel like really often we don't think of acceleration, or slowing down doesn't usually lead to turning around. Because usually when you're slowing down, you're in a car or something, or you've just run a race or something. If you slow down in your car, it's not so that you can throw that thing into reverse and go backwards. And when you run a race, you don't slow down to run backwards. You slow down to stop because you're tired because you just ran a race. But many, many, many things besides the stuff that we do every day, this happens. So it's important for us to understand that if we accelerate long enough, we will stop and turn around and begin to move in the opposite direction. Okay. Let's talk about one more quick misconception. Right here. What is the acceleration? Think about it. Chew on that question for a second. Let me ramble a little bit. Let me wander around so that you can chew on the question. What is the acceleration when we're stopped? I'm serious. Take that thing, gnaw on it, get some gristle in between your teeth. Savor the flavor of that one. What is the acceleration when we're stopped? The obvious wrong answer that students say more often than they'd like to admit is they say it's 0 meters per second squared. That is 100% not true. Remember, acceleration is the rate of change of velocity. And looking at this graph, the rate of change would be the slope. The value of velocity is 0 here, but the slope is still whatever that slope is. There's nothing special happening to the slope just because the graph has moved through an x-axis, right? The slope is still sloping it down right there. So our actual acceleration is the same negative 0.5 meters per second squared here. Stopping does not affect your acceleration. It's just weird for people to think when you stop, you're speeding up or slowing down. That's kind of where the disconnect is, I think. So we'll revisit this when we get to projectile motion, but you need to think about this, maybe puzzle over it, justify it to yourself. Why stopping does not mean you stop accelerating. It just means momentarily you aren't moving, but then you immediately start moving the other direction, and then you're speeding up again. You're going faster, but in a negative direction. So, something to think about. All right, now that we've wandered long enough, let's answer this last question. How far did Antonio go? Far is a displacement. So we need a new equation. This equation tells us absolutely nothing about displacement. Luckily, we have a displacement equation. So let's use that thing. All right, let's extend this page a little more. Okay, so x final equals question mark. X initial, they don't really tell us, so we're going to arbitrarily pick 0. Wherever you start timing, that's where position 0 is. And I get to pick that because I'm the physicist. We could say it's on the surface of the moon, but that would probably make the problem harder, not easier. We want to know how far he went after 8 seconds. His initial velocity, that's important because this equation is x final equals 1/2 acceleration times time squared plus velocity initial times time plus x initial. His initial velocity, what was it? 3 meters per second. And acceleration is negative because we're going backwards, 5 meters per second squared. Now this is a math problem, and we're just going to plug these numbers in. Let's do some quick simplifications. Initial displacement is 0, so we'll just drop that thing. So x final equals 1/2 times acceleration is negative 1/2, or 0.5, either way, time is 8. So 8 squared. Number one mistake students make using this equation is they forget the squared there. It happens all the time. You're going to do it, but I told you about it, so maybe you won't do it as often. Plus initial velocity is 3 times time. This time and this time, they are the same time. They're both time. So this one is also 8. All right, let's simplify some stuff. X final equals a half times a half is a fourth. 8 squared is 64. Plus 3 times 8 is 24, I hope. I think so, yep. A fourth of 64 is 10, what is it? 16? Yeah. So X final equals negative 16 plus 24. X final equals 8. And we're doing everything in meters. So he's going to go 8 meters. He's actually going to go slightly more than 8 meters. But because we've done 2 seconds of going backwards with that negative velocity after 6 seconds, at 6 seconds when he stops, this will be maximum displacement, and then he's going to roll backwards a little bit. So he'll probably make it all the way to like 9 or 10, but then roll a little back. But that's okay. This is his displacement at the time of measuring at 8 seconds. So, all right. What a fun problem. That was nice and crunchy, wasn't it? That one had a nice body to it. It was nice texture. A little crunch, a little crisp at the end there. So tasty. What a great problem. All right, we're gonna call it right there, just because I don't want to overwhelm you too much. I understand physics is overwhelming. So, if you have any questions, be sure to let me know. Otherwise, go try out those practice problems. Give it a taste for yourself. Give it a lick. All right, I'll see you guys next time.